But to start with, I want to ask you a question of how fast is your website? Maybe the website that you're building today for a customer or for your company that you work for. What does being fast even mean? Is it how long it takes to load? But in what context is that? Probably our users all have different contexts when loading it. Being fast probably means many different things in many different contexts. And how do you go about measuring that performance? For years, we've been searching for the golden performance metric, the one that we all need to optimize our websites for. But does that even exist? Should we have a single metric to ascertain how fast our website loads across? But load should just be an experience. It's not a single point in time. And so I would argue that there shouldn't be a golden performance metric, and there definitely isn't one of them, at least, that we should be optimizing for. But reality, most of the traditional metrics have almost nothing to do with user experience. The first bytes, the document complete, how many requests I send out of the way, or how large my files are. And we start to optimize our website just for the sake of optimizing our stack, but none of these correlate to the load experience or actually what the user came there to do. You know, on a news article, a website, that might be the article that I came to look for. In e-commerce, it might be the thing that I want to buy. And search results, it might be the thing that I was actually looking for. That is the user experience, and we should be thinking about how long it takes for that to happen, rather than how long we actually built our page. Load is an experience. There is no single load metric. But luckily, times are changing, and we're seeing a new rise of metrics coming out that focus on human-centered metrics, focus on user experience, the thing that the user actually came to your website to do. And the great thing about these is as we start to optimize them for them, every optimization we make to a human-centric metric is ultimately going to improve the user experience of your website. So things like the speed index, the first meaningful paint, which we're going to look at today, time to interaction, and I can't stress this last one enough, custom metrics specific to your own KPIs and your business needs, and that context of why the user actually came to your site in the first place. So what is TTFMP, or the first meaningful paint, and what does that even mean? To put simply, first meaningful paint is the time when a page's primary content, i.e. the thing the user actually came here for, appeared on the screen. Not when we started painting pixels to the screen, the thing that they came here for. So maybe it's the headline of the news article. Put more detailed, it's the first paint after which the biggest above the fold, so if you imagine a mobile phone, this is the fold, the viewport, the first viewport, because it's highly likely that the thing the user came here for is going to be in that above the fold. Layout change. We'll talk about layout in a bit, and Eric did a really good intro to layout for us as well. And most importantly, when web fonts has also loaded, because I could paint lots of things to the top of the screen and cause lots of layout, but if the web fonts haven't loaded, and I hear we all like to add lots of web fonts to our pages these days, much to my disgruntlement, when they've also loaded, because there's no point, if the user came here probably to read something, we also have to wait for them. And so this is probably represented visually. And first meaningful paint was coined by some much smarter folk than I at Google last year, and they outlined their methodology about how you can go about ascertaining this metric in a white paper. I will share the slides later. But visually, this is taken from the white paper. On the graph at the top, you can see on the y-axis, it's the amount of layout objects, performed layout. So as Eric explained to us, that's the x and y coordinate of the element and its width and its height when we're creating that layout tree. And the amount of those objects that happened correlated to time on the Google search results page here. So as you can see, at 1.5 seconds, Google do something very clever that they flush the head of their document for the search results before they've even sent your search query back to the database. So you get a very fast perception of loading, but actually the thing the user came here for wasn't till 1.9 seconds when the search results came in. And you can see how that directly correlates to the amount of layout objects that are actually painted to the screen. And it's at this point is our first meaningful paint. And that's a much more meaningful metric to our users and their experience than, say, the start render at about 1.5 seconds. Again, it might be better visually represented like this. This is the ft.com homepage. Let's play a little game here. Now that we have an understanding of the first meaningful paint metric, where do we think it is? Is it 3.5 seconds? 4 seconds? Come on, shout some out. 5 seconds? Put your hands up. Where do people think? Put your hands up for 4? 4.5? 5? 5.5? So I think most people thought it was 4 there. On this, it's actually 5 seconds on a 3G emerging market device. And we'll find out how we can go about getting our own metrics. And unfortunately, we haven't yet exposed these new human-centric metrics yet as JavaScript APIs, although there's a lot of work to do that. So at the moment, the only way that you can measure your own firstly meaningful paint is using Google's Lighthouse tool, which they've kindly open sourced. Originally, Lighthouse was built as a way of testing your website, your progressive web app, against best practices for progressive web apps. But then we soon realized that the audits underneath the hood that it was doing are actually very good for any website. So I urge you, if you want to go and work out what your first meaningful paint is now, you can either download it as a browser extension or use it as a CLI tool, so you could integrate it as part of your CI builds. And there's a whole suite of audits that it runs that actually very good at ascertaining how fast your perceived speed is. If you're interested specifically in this metric and the rise of its sister metrics such as time to interaction and hero elements, I strongly urge you to watch this video from Google I/O this year. It's all about how the rise of user-centric performance metrics and how the roadmaps for these are changing and how we are going to try and integrate these types of metrics into our browser JavaScript APIs. Okay, so now we know what the metric is. Let's have a dive in and think about how we can optimize for this metric. And to do this, we're going to apply a suite of optimizations and experiments to a real website. I think it's very easy to break your budgets and prove things using a to-do MVC application, but that's not the type of application that we all build on a daily basis. Does anyone actually build a to-do MVC website for their day job? No. So to do this, we're going to use a real-life website, which we're going to use the Financial Times homepage. And a disclaimer here, they have a very, very good and talented team that focus a lot on and care a lot about the performance of their website. And again, a disclaimer, I used to work there, so they've given me permissions to use their website as an example. And most importantly, I'm really sorry for the Theresa May photobomb here. She definitely doesn't deserve to be on this stage, although she does look like she is a real-life emoji caricature, and it's just a disgrace to my nation, so I'm very sorry for that. So each test that we run, we're going to run through web page tests. Who here has used web page tests? Awesome, it's like the #1 tool in the Performance Ninjas toolbox. But the reason why I've chosen to run our test through this is two very important things. The first one is that there is a real device at the end of this form. And contrary to popular belief, the shiny iPhone or Google Pixel that you have in your pocket right now is not the average phone in the world. In fact, the average phone in the world is a very low-powered to mid-end Android device. So here, a Moto G, we actually have Moto Gs running, physical devices running at the end of this, so you can run your websites through them, and it allows us to shape our networks to real network conditions. The LTE that you get here in New York is, again, not the average mobile connection. The average mobile connection in 3G emerging markets has a 400 millisecond round trip time for a packet, so that takes 400 milliseconds to travel between the client and the server and back again, just for one bit of the request. So imagine your request is made up of lots of round trips. We're going straight into the seconds there. So we need, I can't stress this enough, to be testing on real devices with very poor memory and CPU performance, such as a Moto G, and real network conditions, or that Li-Fi that we all actually do experience on a daily basis. But you need to be asking yourselves these questions, not just the budgets that I'm going to set today. Where are your users based? What is their device landscape for the website that you're building today? No one website that you build is going to have the same characteristics or answers to these questions. In what context are they using your website? A lot of people sometimes tell me, oh, no, but I build a desktop application, and therefore I've only got a single context. And that is a complete bullshit. There are multiple contexts for every website that we build. I use the ft.com on the train, going through in and out of network on the tube in London, on my mobile device, but then I use my highly powered MacBook Pro on my T1 connection in the office at lunchtime. These are multiple contexts for the same user. And again, this comes up all the time here. What did they actually come here for? What is the user experience that you need to be optimizing for and delivering your site as fast as possible? So in the case of the ft.com homepage, we're going to aim for a budget of a first meaningful paint of 3 seconds on a 3G emerging market network condition, 2 seconds on 3G and 1 second on cable using a Moto G to do this. But again, can't stress this enough, you must be creating your own budgets and setting them and testing your websites against your own budgets, not just taking mine as a line in the sand. So that we can measure the impact of every optimization we take to try and improve our first meaningful paint, we first need to set a baseline. And so to do this, we're literally going to have a template like this. It doesn't get as simple as this. This is a vanilla website, as we've all been building since 2006. We have a HTML document that in the head element, we have a link element with a relative attribute of style sheet to a main CSS file. Just one CSS file, referenced normally in the head of your document, and a document containing all the text. I don't care how your CSS was authored, whether or not it was CSS in JS, like I hear lots of people want to do these days, or if you used Webpack to bundle it. As long as it's a single concatenated file and all of my content in the document, that is our baseline. So if we were to run that through web page test, it would produce a network waterfall like this. Put your hands up if you use network waterfalls on a daily basis, or have you ever seen one before? Don't worry if you haven't. So just a quick explanation. On the y-axis, we have the requests that the browser makes in the order in which they were requested, therefore probably the priority. And on the x-axis is time. And web page test, unlike some of the browser developer tools, gives us a nice breakdown of MIME type here using color. So we've got HTML is blue, CSS is green, purple is images, JavaScript is orange, and fonts is red. And for each one of these network requests, it gives us 2 color. So if you look at the HTML, it's a light blue. That was when the request was sent, and the time that we were waiting until we got the first byte, and then the download time as we received all those bytes. And it gives us some markers, such as the start render event. There's not the first meaningful paint, but it's a good indication of when we start painting as this green line. So that's how we read a waterfall from network paint. So if we were to run our baseline test in web page tests against our budgets, we'll see that we have an 8,000 milliseconds first meaningful paint on in a 3G emerging market on a Moto G, which is way past the budget we set. So let's try and break that budget. Our first experiment is going to be to inline our critical styles required for that above-the-fold rendering. And some of you may have heard of this technique before. I've been speaking and advocating about the technique since about 2014 at this very conference, actually. But for those of you that don't know, let's have a quick recap. And to do that, we have to look at our critical rendering path of the page, which is the single path a browser must do to be able to paint to our screen. Again, Eric did a very good job at explaining what the DOM is, the CSS OM, and the render tree just beforehand. So first, from the point at which our user navigates, so when they click on that link, maybe on a Google search results page to it loading, we have to perform the network request, so it's a GET request for our index.html of ft.com. We then start to receive the bytes. Now, HTML has an amazing part of the specification that allows it to be parsed incrementally. We don't have to wait for all of the bytes to come in down the wire before we can construct our document object model. It can happen incrementally as the bytes come through. So we build our DOM, we find that link element that we have in the head of the document, so we now have to stop and go back to the network and perform the networking request for the CSS file. Now, unlike HTML, CSS can't be parsed incrementally, because if you were to paint at the beginning, as you were still bytes were coming down the wire, there may, because of the nature of the cascade, there may be a style declaration at the bottom of the file that overrides one at the top, and you'll have some horrible stuff like this going around your page. So for that nature, CSS is render blocking. And so we have to wait. And so we've created some idle time on our browser main thread here, waiting for that networking to happen. So let's note that. Also imagine that I'm on a train, and I'm on Twitter, and I follow a link to the ft.com, and then I go into a tunnel, or my train's Wi-Fi cut out. Now, I've been given all of the content I needed because I've downloaded all the HTML file, but my network request for my CSS has failed. And so even though we've got all the content, we're sit blocking, waiting on this white screen of doom that you're probably all used to, and a little thing down the bottom saying waiting. We've created a single point of failure by separating our CSS from our content. This goes against everything that we've been taught of styles in style sheets and separations of concerns. And now we don't have enough information. So what if we were to inline the critical styles required for our first meaningful paint in that viewport into our HTML document and declare the rest of the CSS as asynchronous and tell the browser you don't need this yet. And here, we now have a critical rendering path that looks like this. There's no longer a single point of failure on our CSS. So that's what it looks like. Back to our experiments on ft.com, now we have a style element in the head of our document. We've declared the rest of our CSS as asynchronous in a separate file. To do this, I'm using the Filament Group's load CSS. Now, the implementation details don't really matter here. It's more about the concept of inlining and declaring the rest as async. Hopefully, browsers are going to allow us to have link elements actually in the body of the page. So we don't need to do this anymore, but people like Chrome, Jake, still need to sort themselves out when it comes to this. So we're left having to use a technique like this at the moment. But again, don't stress about the implementation details. So if we were to look at our baseline waterfall again, note where the start render line is, because we've had to parse the HTML document, we found the CSS file, we have to wait for all of that to come in before we can construct the CSS object model on the render tree and the layout box, and then we can paint. By inlining our styles, note the difference here of we've been able to paint instantly, and we have declared the CSS as asynchronous. We've tricked the browser into thinking, you don't need this, and I've given you all the styles. Now we have a much faster paint. So you can imagine what this is probably going to do to our first meaningful paint. So we've managed to improve our first meaningful paint for that nice user experience by 63% now, and that's 1,300 milliseconds on cable, on a Moto G, and 3,200 milliseconds. So we're getting close to our budgets already. And with all good things in life, there are some pros and cons to this. Obviously, the cons is that it's not cacheable. Every time we update our critical CSS, because it's embedded within our HTML, we're going to be invalidating the cache of every single article on the ft.com, and that's in the hundreds of thousands. Every time we do that, we're sending the bytes down, even though the browser could cache it in their HTTP cache, but because it's not a separate object, we're not benefiting from that. And it's very hard to maintain. I've worked on some very large websites, and automating this process is not a solved problem. It's something I'm really interested in, so do come and talk to me if you're looking into how to do that. But we no longer have any blocking resources, and we've eliminated that single point of failure that CSS brings. So now that we've been able to get our styles down and paint as fast as possible, let's have a look at how we can prioritize the other resources that are required to let our users interact with our pages and do that thing that they came here for, i.e. your critical resources. Now, I want to have an exercise. If you can think about now is, for the website that you're building today, what is the critical resources required? If you could get rid of all the other resources, but for that one thing, the context that the user came here for, can you think about the 2 or 3 resources you need? I think it's actually much harder than you think, probably, to go about that exercise. So let's do it together. Let's identify the critical resources for the ft.com homepage. Do we think it's the logo? Yes? No? Is it the fonts? Yes. If we remember the definition of the first meaningful paint is we have to wait for web fonts. Is it the hero image of Theresa May emoji face? No? Okay. So fortunately, again, Lighthouse has got our back here. We don't need to do that exercise at all. We can automate the process of it. And they have an audit called the critical request chain. So I can run ft.com homepage through Lighthouse, and here it's telling me that we have a critical request chain of 5 assets. So it was actually the logo for our navigation. It was a lot of our custom web fonts, there's many of them, and it's our main CSS file. So we can automate this process of identifying what our critical resources are and then try and prioritize. And if you take away one thing, solely one thing from my talk today, please let it be this, that you need to identify your critical resources, try and eliminate as many of them as possible. If they do, they really need to be there. And for the ones that are left, prioritize their delivery and optimize those files so they are as small as possible. And that is it. That is the secret to having a very fast first meaningful paint, is you prioritize your critical resources, eliminate the ones that aren't there, and optimize and prioritize the delivery of the ones that must be there. So if we were to remember the methodology for first meaningful paint, it's that web fonts, we have to wait blocking for the web fonts to load, i.e. before we have any text on the screen, before we get that metric. But if you were to look at the waterfall here, fonts are prioritized very low down in our waterfall, much lower than some of the images that are below the fold. And why is that? If they're such a critical, important resource for our user experience, why are they prioritized so low? And to do that, we have to go back to our critical request chain and understand how the browsers work again. So we go and fetch the HTML, then we go and fetch our CSS. And as Eric explained, the CSS object model, that's a tree-like structure, just like the DOM, get combined together. So the CSS object model will look something like this. It will say, oh, we have the root body, then we have a div, then we have a paragraph. And the paragraph has a custom font of 1 and a color of red 2. But the CSS object model will also say, oh, but that paragraph is display none. So when the CSS object model is combined with the DOM, that paragraph will not be left in the render tree. The render tree is only the elements that are going to be painted to the screen. And why did I go on this digression here? Is at that point, and only that point, during the render tree construction, that the browser will initiate the fetch request for a font. Because by their pure nature, fonts are very large and expensive files. And if I was going to not show my paragraph with red text of custom font 1, then why should I go and perform the networking for it that could waste a lot of resources? And so fonts are known as a hidden critical resource. And the reason why they're hidden is the browser will not find out about them until the render tree. So we've wasted thousands of milliseconds waiting because the browser doesn't know about or won't dispatch the font requests then, even though they're such a critical resource to our user experience. So fortunately, the Web Performance Working Group have got our back here again. And they've defined a new API called Preload. And what Preload allows us as authors to do is to indicate to the browser what are the critical or hidden sub-resources, especially like fonts that may be hidden from the browser until a much later point, so that the browser can then go and prioritize the networking for those requests. So to put simply, it provides a declarative fetch primitive that initiates an early fetch. It's kind of up to the browser if it does initiate that request. And it separates, most importantly, it separates the fetching of that resource from its execution. So this is also very, very powerful for things like JavaScript. If you wanted to load a secondary async Webpack chunk or bundle or your React vendor file, this is amazing because it allows us to go and fetch that, but the JavaScript won't be executed, which will help us with our first meaningful paint and time to interaction. So this is what it looks like. We now have 3 new primitives. One is the link element in our HTML. We have JavaScript. We can dynamically create these. And I think this is really powerful. That's often overlooked in the industry at the moment with Preload. So if you can imagine that once my page is loaded and the app is booted in, I have a user that's hovering over a carousel. And when they click on that carousel, it's going to open up loads of images in a carousel. So you can imagine as the user hovers over the button, before they even click it, you can dynamically inject lots of preload elements to go and fetch the JavaScript or the images required for that. So when they do click it, it's going to be an instant lightning experience. So not enough people are using the dynamic version here. And my favorite is obviously the often overlooked link header that we can have on a response of our HTML response. So when I perform the GET request for the ft.com homepage, the HTTP response of that can be decorated with link headers saying, here are my critical resources. And so that's the technique that I've chosen to use for our example of ft.com here. The 5 or 4 critical resources that Lighthouse identified as my critical request chain, I'm now decorating my HTTP response with them using the link header. And there's two important points to note here. First, remember always that fonts need to be declared as cross-origin because the browser still deems them to be, which is a bit of a crazy thing, but it's the truth. And the no push attribute, I just want you to remember that for later on. But this is how I can decorate my HTTP response of my HTML file to say, here are the critical resources. So again, if we look back at our previous example, you can see where the fonts are. They're so low down in the priority here. And if we just by applying our link preload headers, look at what that does to the prioritization of the fonts. And so hopefully you'll start to realize what this is also going to do to improving our first meaningful paint metric. We've been able to prioritize the delivery of those resources. And so now using our preload technique, we've hit our budget of 1,000 milliseconds on cable, and we're very close on 3G on emerging markets of 3,100 milliseconds. That's a 65% improvement from our baseline. But again, it has some pros and cons. It allows us to indicate those hidden resources that browsers might not know about, but it's really easy to create contention and congestion on the network. You can imagine a developer will just go, okay, I'll decorate all of the images that I have on this page in my link headers, and the browser's going to go and try and request them all at the same time. And if you're going to do it either via the HTTP or the HTML version, it requires some custom server logic to do that decorating of your resources. So we could just stop there. We've improved our first meaningful paint now by 65% from our baseline. But surely we can do more. And one such technique is HTTP2's server push. For the first time now in over 20 years, that's how amazing the HTTP specification is, that they didn't really need an update for 20 years. We have a new version of the underlying transfer protocol of the internet. And I could do a whole talk on this subject, and I have, and I urge you more to go and check it out if you're interested. Again, could you just put your hands up again that Vitaly did at the beginning? How many people are using H2 in production here? So yeah, he was really right. It is only about 8 to 10% of you. So I urge you to go and have a look. So let's go and look at our traditional request and response flow again for that web page. First, the browser performs a GET request. The server then probably has to process that request. It has to go and do some templating and go and make some database lookups to generate the HTML response. It then sends that back with a 200. We then start to parse that document build-up. We find a CSS or a JavaScript being referenced, and we have to go and perform the networking for that again. But all during this time, when the server was processing, there was a lot of idle time on the connection. We weren't using the connection at all, where we could have been sending bytes back and forward. So what if the server could predict that the next resource that you're probably going to request is that main.css file, and then push or flush those bytes down the wire whilst the server is doing its think time? And HTTP2 calls that a push promise. So now HTTP2, instead of having multiple TCP connections open, we now only maintain one stateful TCP connection between the client and the server. And we can multiplex. We have a new binary data framing layer that allows us to interleave different frames. And so HTTP2 calls this a push promise frame. So all it is a very small data frame that gets sent down the wire saying, I am going to send you the main.css file. Don't request it. So you're making a contract between the client and the server, a promise of saying, I'm probably going to send you all these bytes. Don't request it. And so we can now programmatically do this. But the semantic that we've chosen in the industry is to use our friend, the link preload header, to decorate all of the resources that we want to be pushed. And note, remember I told you earlier on about that no push. If we remove that declaration, any HTTP2 server that's enabled with server push potential will, I think all of them now, the ones that do, will use the link preload header as that indicator of, I want you to push this resource along with my HTML file. And so going back to our ft.com example, now because we no longer need to inline our styles, so we're going to get that benefit of it being cached. So we've actually replaced the inline style declaration with a critical CSS file that we are pushing along with the document, and then we've made our non-critical styles async. So let's take a closer look at what's actually happening on the network connection before we apply this optimization. So we make the request. We've got some idle time at the beginning during server think time. We then get our index HTML file. Because we've inlined, this is before we apply the optimization, we have a very fast start render and a first meaningful paint. And first meaningful paint is weighed whilst we're still waiting for the non-critical styles to come in. And this is great, but you may be surprised what happens when we apply our technique and push the critical styles and don't inline them. We've actually pushed back our start render and our first meaningful paint by quite a dramatic amount. And why is this? So we haven't used up that idle time. We got to the index.html, and then we got our critical styles, even though they were pushed. And why is this? We're not using that server think time. That server push was being the holy grail that we've been promised that it would be. And to do this, we have to look at a bit of understanding of how HTTP2 servers work. They use something called a prioritization tree to determine the order in which it will flush bytes down the connection. And even though we told the server to push our critical CSS, because we did so doing a link header on the response of our HTML file, the HTML had already come. We're not using that server think time. So now the HTTP2 server has all of the HTML and all of the CSS. And the spec of the prioritization deems that HTML should, by quite rightly, have a higher priority than CSS. So it's going to flush all of the HTML bytes down before it does the CSS, which is why we got them in the wrong order. And just to stress, this behavior may be different depending on your H2 server implementation, but the majority of them work like this. And we don't have any clients yet, apart from Firefox, that are actually doing correct prioritization in the opposite direction. So let's look at our waterfall here. Now, because even though it's pushed, you can see that we don't have a light screen on our critical CSS file because it came after our HTML bytes, and previously our HTML bytes contained all of our styles. We've actually delayed our first meaningful paint. And so that's only a 43% improvement on our ft.com homepage. So we've actually had a negative effect by using HTTP2 server push. Now, it's part of my job is I have to do research of things like this. And I was very happy that 2 weeks ago, Jake wrote an amazing blog post detailing all the research that I was meant to do myself on how browsers are interacting with H2. So I urge you, if you're interested in this, to go and read this. It's an extremely detailed blog post going into all of the intricacies on most of how browsers are behaving with server push at the moment, such as things like there's weird things that they're not correctly sharing the server push cache in between requests or sessions. And so you actually get a much worse effect than you were hoping for. But the question that I want to pose here, though, is the problem here is indicating which resources to push via a HTML response, with the HTTP response, using decorating it with a link preload header, in fact, much too late, because then the server will have all the information it already needed. So we're not utilizing that idle connection time. So how can we really achieve that holy grail that push has been promised to us as? And this is what at Fastly we're calling async push. So let's take a look at our network utilization again. And remember that server think time, whilst it was generating the templates, that is the holy grail of where we really, really want to be pushing. And so a much more common architecture these days is that your HTTP server will be decoupled from your application server. So think about, say, if you have a Node server that's actually generating your templates, it's highly likely that you'll have something like Nginx or Apache or a CDN or a load balancer sitting in front of your application servers. And because of this architecture, it allows us to decouple the HTTP2 server pushing from the application generation. And so let's have a look here. Now, if we have programmatic access to our network connection, that's how we'll be able to flush bytes down the wire. And again, I must stress the implementation it doesn't really matter here. It's more about the concept of what we're doing. So here we're using Node's HTTP2 module. And if you imagine this is an Express-like middleware handler. The first thing we're doing at the top of the request handler is on our open connection is we're pushing the CSS down way before we fetch data from our database or render any templates. We're using that idle connection time. So if we were to apply this technique to the ft.com, you can see that we've reached our holy grail here, that our critical CSS is during the light blue phase, the think time, the idle time of our HTML. So now the browser has all of the information that it needs before it's received a single HTML byte, and we can have that instant, fast user experience that we've been hoping for. And so with async push, we've been able to have our best improvement of 66% of our first meaningful paint now. Again, it comes with some some pros and cons. The pro is that we're using that idle time, but it's really easy to create contention on a network. We only should be pushing potentially our CSS or our core JavaScript bundles if we're not doing server-side rendering. There's limited availability for this. Your architecture depends on it. You have to do some custom server logic, so it's hard. But I think this is an area that I'm really interested in seeing both clients and servers improve on over the coming years. And H2 push is very, very hard to debug. If you want to find out more about async push exactly, we've released a blog post last week about how we're doing async push. Again, the implementation doesn't matter. It is the concept of using async push. But what about the repeat view? We've talked here a lot about that first load experience. We haven't talked about how we can optimize for the repeat view. And some of the major problems here is like the client will already have most of these assets that we're preloading or trying to push to in their HTTP cache. And so I want to show you how new technologies such as service workers and the purple pattern is going to solve this. But I've run out of time, but fortunately both Liza and Jake, Liza today is going to be talking about service workers and Jake about how we can use them to optimize loading for repeat view at this very conference. So hopefully they're going to go hand in hand with this talk. And we talked a lot about CSS and fonts and other critical resources. We haven't talked about JavaScript. And we've talked about that first meaningful paint, but a lot of people are starting to use React and not do server-side rendering. But the interesting thing here is that all of these techniques, even if you're using something like React, can be applied to optimize the delivery of your JavaScript. So if that is your core resource, then yes, you should be using link preload or push to deliver those assets. Going back to my point of the one thing to take away from this talk is identify what your critical resources are. It might be your React vendor bundle and prioritize the delivery of that. Also, First Meaningful Paint has got sisters and brothers of many other metrics, specifically something like time to interaction, where we're measuring how long it takes for our JavaScript to boot up and the user can actually interact with. And again, tools like Lighthouse expose that data for us. So using a combination of techniques that we've learned today and we've applied to the FT.com, we've been able to achieve our goals. So let's briefly compare actually what that feels like as a user experience. Again, this is a human-centered metric. So we have the baseline at the top all the way down to async push here. But that's probably better represented as how the user actually experienced it. So see, this is on a 3G emerging market, on a Moto G again. Feel how fast the push async with preload was compared to our baseline. And whilst we've got a strong toolbox of APIs emerging that we've seen today, there's definitely a plethora of APIs that are coming out that really excites me. We've still got a lot of problems to come, but fortunately, the future is looking bright in this area. The first one being is that we outlined the biggest weakness of server push was that we're using the link preload header to decorate what we wanted to push. And this is far too late in the connection state. And this is where my colleague Kazuo has suggested the 103 status code that's now in IETF working draft specification. And 103 allows a server to flush an early HTTP response whilst it's still generating your actual file, that any intermediaries or a browser can then use that information, so such as a preload header, to go and warm up any caches that it needs to, or go and get that before the server responds it. So it's a secondary response. 100 is the information status range, if none of you knew that. I definitely didn't know that until a couple of months ago. And I think this is going to be amazing, that making much more use of idle times, and most importantly, intermediaries like CDNs that are enabling us to take advantage of this type of state. And the second one that really excites me even more than that is cache digest. We mentioned in the push example again that it's very easy to waste bandwidth. Once I've pushed a resource to the client, on the second request, they've already got it in their HTTP cache. So there'll be no point in me pushing it again. But as a H2 server, I have no knowledge of what the client has actually got in its HTTP cache. And this is what the client digest specification is going to solve. So it's a new data framing, again, over HTTP2, of as the client initiates the request with the server, it also sends along another payload containing a digest of all of the resources that it has in its cache for that origin. Obviously, because of security, it needs to be for that origin. Then the server can choose to use that information. Okay, all right, I'm not going to push that CSS file because the client's already got it in his cache. And these two new specifications combined together is going to be really, really powerful and allow us to be much more efficient in how we utilize the bandwidth and deliver assets to our users. So this has truly been a whirlwind tour of asset loading in the browser, and I've only kind of scratched the surface on some of the techniques, but I hope I've given you a suite of toolbox and techniques to apply to your websites when you go home. And please do get in contact with me on Twitter if you've applied some of them and they're working out well for you. But I just wanted to leave you with some points that resource loading in the browser is hard. It's much harder than we probably thought it was. Bandwidth is definitely underutilized on the network. We're wasting loads of time in the way that both browsers and services are architected, and we're not using our network utilization as much as possible, especially on mobile. So identify your critical resources in your request trains. Use tools like Lighthouse to do that. Once you have identified them, use APIs such as Preload to indicate the critical resources and hidden resources to the browser. Push things like critical CSS or your critical JavaScript, but only on that first view and only in idle time. So try and use techniques such as async push to do that. But most importantly, always be testing. There is no single context, as I hope I've got that point across to you today. Every website is different. Every critical request chain is different. You need to be doing these testing on real devices on your own websites. Thank you very much.